It is recorded, so don't worry, and we will post the recording as usual to our YouTube channel, and I'll share the link here in just a bit. Couple of housekeeping items. If you do have questions in today's session, feel free to use the chat window. Please switch to posting to everyone so we can all see your questions, and also for everyone on the panel who might be answering, also make sure you're switching to everyone so we can see questions and answering in the chat going on. All right, so my name is Antje Barth. I work as a developer advocate at AWS, and I'm running these webinars every month together with Chris Fregly, and Chris is also on the line. Good morning, Chris.
Good morning, everyone. Thanks for coming.
All right, so just a quick intro here before I hand over to today's speakers. Chris and I, we've been authoring an O'Reilly book, Data Science on AWS. And as part of that, we're also running those monthly webinars. We had run a couple of workshops throughout the year as well, showing a lot of the content that we also have here in the book. And we're recording all of the sessions. So if you want to have a look at those and you couldn't make it in this year, have a look at the YouTube channel. And I'm going to post here just quickly for everyone in the chat window the link to the website, datascienceonaws.com. And here you'll find a quick link to the book if you're interested, and also to the YouTube channel where you can find all recordings of the previous meetups and also of the workshops we've been running this year, and also to a public GitHub repo that contains a lot of code samples that we talk about here in the book and that we base the workshop on as well. And just as a quick update here, in case you have friends, colleagues in Japan, we just announced and published the Japanese translation of the O'Reilly book. So super exciting. It's all translated to Japanese. So if you have friends there, colleagues there who might be interested in reading this book in local language, feel free to also share that link with them. I'll post here also the link here in the chat window to the Japanese edition. And there will be more translations coming out, so stay tuned and follow us on Twitter, on LinkedIn. We will make sure to post it once we have additional languages ready. And with that, let's switch over to today's session. We do have a packed agenda, as I said, and I'm super excited. We have 3 guest speakers today. The first one is Russell Kaplan from ScaleAI, and he will talk about how to tame the long tail, about solving edge case failures in production ML models. After that, we have James Jory from AWS, and he will talk about hyper-personalized recommendation systems, and also gives you a quick update on what's new with Amazon Personalize. And then for everyone interested in NLP, we also have Mia Chang with us, also from AWS, and Mia will give you best practices and tips around how to optimize your NLP inference. So hopefully we have a bit of everything for everyone in today's meetup. And with that, without further ado, I'll hand it over to Russell, who will kick it off. And Russell, if you want to do a quick introduction of yourself as well before we start, and then the stage is yours.
Thank you so much. Great to be here, and great to meet you all. My name is Russell. I lead the Nucleus team at ScaleAI, which is our dataset management tool that helps teams improve their ML models by improving their datasets. I joined about a year ago when Scale acquired my computer vision startup called Helia, which was working on similar tools and infrastructure. And before that, I was a senior machine learning scientist at Tesla on the Autopilot team, where I was responsible for the core vision neural network. And then I was a researcher in the Vision Lab at Stanford before that, focusing on automatic image understanding. So yeah, thanks for having me. Super excited to talk a little bit more about kind of long tail debugging and solving these edge case failures in production. I'll go ahead and share my screen. And I believe there is time for a Q&A at the end, but also feel free in the chat to ask questions as they come up, and I'll do my best to answer. So to get started here, the title of this talk is Taming the Long Tail in Machine Learning. And I've already given a little bit of background about myself, but as a little bit of context to add, here at Scale, we kind of work with lots of different customers at different stages of ML maturity. And what we see is that as customers sort of move up the production maturity spectrum, they consistently encounter ever rarer edge cases that sort of flummox ML models in production. And in an autonomous vehicle setting, this type of failure is very well known. Rare situations like a unicyclist or pedestrians behaving in a very unusual manner. But it doesn't just happen in autonomous vehicles. It happens in any situation where machine learning is powering a product that people are interacting with. And the big challenge has been, in many cases, when you have an ML-powered product, a user will report an issue or a bug. Maybe that user is a safety driver if it's an autonomous vehicle, or maybe that user is kind of an end customer of some product that you've purchased. And it's really challenging for ML teams to go from a bug report to a fixed bug due to the inherent nature of how we develop machine learning today. And so the purpose of this talk is to go into the sort of workflows that we've seen start to be most successful for, is my screen shared? Al, can you see my, can everyone see my screen?
Yes, I can see your intro slides.
Perfect. Perfect, okay. Yeah, so the purpose of this talk is to go through sort of an emerging set of workflows and best practices that we've observed both internally and externally to help teams kind of tackle issues like this. How do you go from a bug report or an edge case failure to first diagnosing the problem and second fixing the problem? And as a teaser, the answer is in kind of data set manipulation and in data set management is where we've seen sort of the highest leverage. Okay, so Angel says he can't see slides either. I'm on a slide right now called long tail distributions. And it looks like, many people cannot see slides, but Antje, you can see slides?
I can see the slides coming through, yeah.
Okay, it looks, now it's visible.
Yeah, it's coming through. Great. I think it was a little bit confusing with your image picture, maybe.
Oh yeah, there's a slide. Okay, great. Okay, cool. Great, thanks everyone. I will continue to monitor the chat, so please feel free to ask questions. I wanted to just start quickly. What do we mean when we talk about a long tail distribution? So one example would be on the Berkeley Deep Drive dataset, which is an open source dataset from Berkeley for autonomous driving. And this shows a very classic pattern that we see in almost all real world data collection settings, which is that some classes are exponentially more common than other classes. And this is great for having machine learning models work well in those common classes, but is notoriously difficult to learn those classes in the tail of the distribution due to the way that supervised learning methods today depend on many different examples to learn meaningful representations of each class that you're evaluating on. And this problem of data collection, it's sort of the top of the funnel of an issue that then manifests throughout the stack all the way into the end application. So this is an example of kind of a machine learning model that was naively trained on the rider or cyclist class in Berkeley Deep Drive, having a lot of trouble. The red bounding boxes here are the predictions of cyclists compared to the green ground truth cyclist annotations. Having a lot of trouble detecting these cyclists in common cases and edge cases due just simply to the fact this is a rare class. And this is behavior that out of the box people see very frequently when training a model on kind of any sort of imbalanced data set. And there's a whole family of techniques for how do we address this, right? And we'll go into that a little bit. But the first and foremost kind of issue that this poses is that it actually makes things really expensive because the easiest way to fix this issue, sort of simplest, is to just go collect more data. But the first order mechanism that people use to do that involves kind of the same sampling strategies that maybe you've used to build that initial data set. And so if you just kind of pay more money and add more data, eventually you're going to get a few more examples of cyclist coverage in this case in your data set, but those costs grow exponentially for linear gains in model performance. And this is something that I think many people have a bit of an intuition for, but it's worth really explicitly hammering home, which is that model performance in AI exhibits diseconomies of scale. Grinding out that extra 1% once you've already done a fair amount of work is exponentially harder, both from a data collection perspective and from sort of model improvement perspective. And many people would argue that this is one of the reasons that we've been talking at least about autonomous vehicles for more than a decade, and they're still not really here yet. This long tail is just really, really hard. And yet at the same time, we've sort of learned a lot in the process of working on these problems of how can we change the cost equation here a little bit, and how can we change the model performance equation to be a little bit more clever in improving our systems. So I would say the status quo today that we see teams, that I see teams kind of most oftenly engaged in, is this endless loop of experimentation, where you've kind of collected some data and then you've maybe curated it, which is probably the most important step, and we'll go into more later, sent some of that off for labeling, trained a model, and evaluated it. There's a question here on, would augmenting data for the classes with less data work here? It's a great question. And absolutely, that should be one of the sort of standard tools in the toolbox that anyone reaches to for improving rare class performance. Usually where the sort of highest leverage improvements are before you even worry about data set changes would be, as Angel is suggesting, kind of rare class augmentation, would be oversampling of rare classes so that they just show up more in training, which can potentially lead to overfitting if you don't have enough data, but it's usually better than not. And potentially using loss weighting as well, so that you find kind of greater gradient penalties for the sort of rare images in your data set. But of those, the more data, the more data that shows up, the more, the better your model is going to do on that edge case. And yeah, as a quick reminder, when people ask questions in Zoom, please change the host and panelists selection to everyone so that other folks can see your question. And thank you, Antje, for reiterating that. So as teams end up in this loop of experimentation, the most important part is to think of this as an iterative process of not just we've trained a model, we've deployed it, but the deployment as really the first step in a much broader campaign for the greatest effective data collection you can do to mine the long tail. And using data set curation to mine the long tail is the cornerstone of improving model performance in these tricky cases. We are fortunate in that most of the time, when our models are deployed, if we do have issues with rare classes, a lot of times that's something that we can then source. We can take that data that we're seeing in production, collect it, and hopefully include it in another round of labeling. And I think too often we still view sort of the data set as something that's static. We've got our train split, our test split. Now we're kind of iterating on the model. Versus in practice, what we've seen is that the kind of highest performing teams in machine learning almost view it as the opposite. You've set up a model and some infrastructure, and the model is static, and the data set is what you iterate on. So you figure out, okay, where does my model need help? Just with the same set of architecture and hyperparameters, and then invest that same energy in collecting more appropriate rare data, getting it labeled, reevaluating, reassessing. So that's what we've seen. And I wanted to kind of, drive home this point that there's an implicit assumption here, which is that not all data is created equal. And this is something that we see very, very true. It's a little bit hard to measure how valuable is one example. And so oftentimes when we talk about data sets, we don't really talk about sort of the diversity of the data or the coverage of the data. It's much easier to think, oh, this is a 1 million image data set, or oh, we have 10 billion text tokens in what we scraped over here. But the reality is that because data follows long tail distribution, there's also a similar sort of inverted long tail in value, where common data, for example, in the self-driving setting, maybe you're going down a highway in a relatively common environment, that data might be exponentially less valuable than seeing an RV in an unusual pose or something that your model has struggled with in the past. To the point where many teams will reach the mode where they deliberately avoid random sampling at all for data set building. Random sampling being the enemy, because you're actually biasing your collection of data to the data that's not valuable by definition, and really explicitly instead focus on edge case mining. And that's what we see in kind of phase 2, phase 3 of machine learning lifecycle and production, is this shift from kind of random sampling to really curated, targeted data set building. And so this is on my mind a lot because I work on Scale Nucleus, which is this dataset management platform people use to do this. And I thought it would be helpful to, rather than kind of make some slides about what could this workflow look like. I'll sort of just show you one instantiation of it in Nucleus, and then we can sort of discuss from there, what are the implications of this, and how can you kind of measure your own success in improving and solving these like long tail issues. And then the second important piece to touch on here is, once you do this, how do you make sure those issues stay fixed? And we'll talk about kind of parallels between CI for code and potentially what would a CI for models look like sort of at the end of this talk as well. So I'm going to go ahead and switch over to kind of a demo. So again, feel free to kind of ask questions as we go through here. So this is that data set we were talking about, Berkeley Deep Drive in Nucleus, this data set management platform, which is designed to make it easy to kind of visualize and explore your data, find where the bugs are with your model, and then figure out how to kind of curate your data to fix the problem. So a typical workflow we see, not just in the self-driving setting, but in many settings, is that, again, these deep dives, they start with a bug report. They start with an issue some users having with a model in production. And so in this case, it might be that a safety driver was reporting that they had to intervene very frequently when there were trucks at nighttime. So they're asking the machine learning team, hey, what's going on here? Can we fix whatever this behavior is? So how would you want to debug an issue like that? Well, the first thing to check is, okay, well, how bad is our long tail problem? What does our distribution of trucks look like compared to other classes here? So I can see in this particular data set from Berkeley Deep Drive that we follow this sort of classic long tail distribution here, and there's around 34,000 individual truck annotations. So that's actually enough data that, even though it's not part of the head of the distribution, we should be able to learn something about trucks in this. And so it doesn't quite explain the issue that's going on. So we can actually click in on this part of the plot to zoom in on sort of just the subset of data that contains at least one truck. And this is useful. Now we can start to look at a lot of images that contain a truck and get a sense of what this sort of region of the data distribution looks like. But it's insufficiently specific because we're told the issue is happening at nighttime. And so one of the next things to do would be to actually filter down this query further based on metadata about the time of day. And so one of the core parts of Nucleus is that we'll sort of index the model predictions, the ground truth, and any structured metadata that exists for the images or other types of data that you have to make it easy to sort of query and explore these subsets of data. And this is really useful because, I think it's often very tempting to sort of just look at plots in TensorBoard and kind of mean average precision scores and see numbers go up or down. And not really have an intuition for exactly why that's happening. And what I would say is that both in my personal experience as a machine learning practitioner for several years and in the experience of many of the folks that I get to work with now, so often there are details hiding that you wouldn't even think to ask the questions for without doing lots of visualization and analysis. And so probably the first valuable part of any new machine learning project is to just spend a lot of time looking at your data without being really sure what you're going to find. In many cases, there'll be really valuable surprises that you can then use as insights to improve performance. And so here we're looking at just this sort of subset of data that's at nighttime with a truck. And this is useful for visualization, but we're really doing this for the purpose of debugging our model predictions. So it'd be very useful, in addition to seeing our ground truth visualized here, if we could see some model predictions shown as well. And so, at least in the Nucleus case, this is a developer product. It's designed for developers and for machine learning engineers. And there's a full API to add your own kind of model predictions into the platform. And so when you do that, upload, hey, here are all my bounding box predictions, or here are all my other types of predictions in kind of a few lines of code. And you can also follow along this kind of after the talk, by the way, as well. It's free to get started on the website. We'll be able to go over here and kind of view those predictions alongside our ground truth. And so now we can start to see, and I might even zoom in here. Let's zoom in a little bit and see what's kind of going on with our data distribution. We can start to see issues kind of right away. So here the predictions are in the sort of dashed lines and the dashed red lines, and the ground truth is in green. And if we kind of look at even just this example, I'm noticing a false positive on the hood where we're predicting a car incorrectly. You can imagine how catastrophic this would be for a control stack if you think a car is right in front of you, when in fact, none exists. And so, we might even want to select this example as, a tricky case. It looks like we're also mispredicting something on the hood over here. Hey, these are cases that we have to watch out for. Looks like another one over here. And build this up into a subset of data that we care about specially. And this is the next big part of long tail debugging. It's no longer sufficient to treat your data set as one large data set. Instead, we see the most effective teams kind of moving to treating their big data set as actually a collection of many scenarios, and starting to track performance on each scenario independently, as opposed to just an aggregate test set, because the aggregate test set masks a lot of the details of what's going on and dealing with those bug reports and getting these issues fixed. So I can create what's called a slice in Nucleus, but it's really just a curated subset of data, like mispredictions on hood. And now I'm tracking this as sort of an independent subset of data. It's something I can kind of export via API. We'll later talk about, looking at metrics on kind of just this subset of the sort of mispredicted hood data, and the ability to then, share it with colleagues and view improvements over time, just to kind of this subset. But what that workflow that we just went through it's a very qualitative debugging workflow, right? We're sort of looking at lots of individual examples and just sort of noticing issues. And so the next important part of long tail debugging is to think quantitatively as well and see, hey, where in my overall distribution is my failure mode concentrated? And so in Nucleus, one way to do this is to go back to these insights, and instead of looking at them for ground truth, to look at them for model predictions. And if we look at them for model predictions, we can start to see automatically computed error metrics that take a diff of what's going on in the predictions and what's going on in the ground truth. And so one example of this is a confusion matrix, which many of us are familiar with, but as a quick refresher, is showing the agreement or disagreement in each prediction and ground truth annotation in the data set, and where we're kind of getting it right frequently and where we're getting it wrong frequently. So we can see, like, oftentimes when the ground truth is labeled a truck, we are predicting a truck. And this confusion matrix is not square, which is the more common version, because often in the real world, the taxonomy of what we're predicting at any given moment might not exactly line up with the taxonomy of what we have labeled, and that's okay. We can also look at how tight are the bounding boxes that we are predicting, and are we having issues maybe with really loose bounding boxes in some cases? What is the intersection over union, which is a measure of that overlap distribution in this data set? What is our precision recall curve, either an aggregate or on a specific slice, and in all classes or for specific classes? And so these tools are useful to again, see metrics and understand how the model is doing. But the challenge is, if you just rely on these plots, it's insufficient to really develop that intuition for why is the precision recall curve not better? Why is it the case that it looks like a motorcyclist is being confused with a person some subset of the time? And so it's really important in any workflow to be able to go from the aggregate to the specific and see what are the examples where this failure is happening. So in Nucleus, the way this is achieved is just all the plots are fully interactive. So we can click on this cell and look at every case in our data set on kind of an object by object basis of where have we labeled a motorcyclist, predicted a person with at least 50% intersection over union. And we can start to see these examples. And we can see many of them are pretty blurry. And that's because these are going to be predictions that are maybe a little bit more farther away from the camera in the image. And I can see here, this is a good case where this is clearly not someone, who's a pedestrian. They're in the bike lane riding some type of, wheeled contraption. Is that a motorcycle? Or probably not. It's more like a bicycle. So that might also be kind of an issue with our annotations. But if we look through in here in more detail, we can see many of these cases are definitely kind of motorcycles that are just being sort of mispredicted as people, right? And we can even hide the predictions for a sec to make clear, yep, definitely a motorcycle, and yet the person is definitely mispredicted here. And we can go through this and see a lot of these examples and start to develop confidence and an intuition for this part of the long tail. What does it actually look like, and why are these failures happening? I see there's a question: can object detection here classify long tail like optical reflections, refractions from real objects here? That's a great question. I will talk later in this talk briefly about workflows for mining a specific type of failure in more detail. But yeah, we would use this workflow to discover these failures in the first place, and then to mine them in more detail. That's kind of the next step. So it's a good question. Very briefly, I also want to mention, when you do long tail debugging, it's not enough to just look at model failures. You also have to consider the possibility of data annotation failures. And so using a similar type of query, we can change the parameters around to be much more likely to find cases where actually the annotations are the thing that's incorrect. And so you can see in this query, I filtered for just the labeled subset of my data, where I'm predicting a car, but it's a false positive. And furthermore, I've taken all these results and I've sorted them by confidence in descending order. So what we're seeing here is cases where our model is really sure there's a car, but the ground truth says no object exists. And if we look at these examples, almost all of them look very much like cars, to me at least. And so we can again ask ourselves, what's going on in this edge case? And if we click on one of these examples, sure enough, if we kind of hide the prediction to make it super clear, we can see this is in fact an annotation error, right? The annotator just kind of forgot to draw a bounding box here. And this is really problematic because you end up, heavily penalizing the neural network for doing something that's actually right. And so kind of part of the sort of way to solve the long tail is to make sure that your long tail is annotated correctly, right? Have efficient kind of model assisted QA procedures so you can cover those edge cases. Often what happens is actually there's an ambiguity in the labeling instructions. And that gets manifested in inconsistent annotations in some edge case. In this case, we can see, though, this is a relatively unambiguous case where it's simply, in an edge case, it's simply an annotation failure. Same here. Here, this is obviously another car where we're predicting and not annotating it. And so you see, this is real data from a public data set that many people, publish papers on today. And this is not at all uncommon. You look at any public data set, and probably your own data set too, if you haven't been careful in using tooling like this to check the quality of those images, or the labeling provider hasn't used tooling like this to ensure the quality before delivering them, then you're very likely to have issues like this. And so kind of getting them fixed is a very efficient path to improving model performance in the long tail. So I do want to then talk quickly about how do we actually solve these issues once we encounter them. And to solve these issues, there's many different approaches as we discussed. In fact, you can even fix the annotations in some cases like this. But most often, the right thing to do is to get more data like the cases that you're struggling with. So I want to talk about sort of one specific example of a case we saw recently where someone was doing some long tail debugging for why they were mispredicting kind of traffic lights on top of vehicles sometimes. They were getting all these sort of false positive traffic light predictions, and it was actually just a vehicle. And using the debugging tools like Nucleus, they were able to discover that this was actually a case of police car lights being mistaken as traffic lights. So you make this observation using some debugging tools. You've found the part of the long tail that's causing problems. Now we want to fix it. And so what's the fix for that? Well, the most natural fix is to just find more images of police cars. Prioritize them for labeling. You're going to teach your model, hey, this police car light is not a traffic light, and it's going to learn that over time. The challenge is that you probably don't have metadata already that lets you query, hey, show me all the police cars in my data set. Otherwise, you'd already be predicting that and you probably wouldn't have the issue. So how do you deal with this when the part of the long tail you're having trouble with is not in your taxonomy of what you're labeling or predicting? The most efficient way that we see is to start with a single example and then boost it. So here I can find, here's just a single individual example where there is a police car in the image. And I can select it, and in Nucleus, I can find visually similar images by running kind of a similarity search. And the way this works in Nucleus is we'll generate model embeddings based on the raw pixels in the data set. And we'll then use those as the basis of any type of similarity search. You can also provide your own embeddings if you have a model that's producing embeddings yourself already. So from here, we can see, okay, yeah, these are many cases where there are, in fact, other police cars. This is great. I could start selecting these and saying, yeah, this is like what I'm looking for. let's go get these prioritized for annotation, right? Because the data in here is data that contains images of both like labeled data and unlabeled data. But this is a manual workflow. We're kind of selecting these one at a time. It's insufficient for sort of large scale mining. And so very briefly, because I know I want to do leave some time for questions, and also please feel free to ask questions in the chat. I want to talk about how you can discover this issue once and fix it permanently. And the idea in Nucleus is to create what's called an auto tag. So an auto tag, it's a way for me to interactively label my entire data set with very high scalability using kind of machine learning in the loop in a bit of a sort of weak labeling setting. So by just selecting a few examples, I'm shown cases that are also visually similar, likely to have police cars. But unlike a similarity search, here I can actually refine the results and I can say, yeah, this is what I'm looking for. But this is actually not a police car, even though it has a blue stripe and it looks kind of similar. Same with this, these aren't police cars. So I'm not going to select those. And by not selecting them, I'm actually teaching a machine learning model that's being trained under the hood right now that this is a hard negative example. This is not what I'm looking for, but it looks similar. And if I hit continue refinement, Nucleus takes those positive cases as, hey, this is what I was looking for, and those negative cases, this is what I wasn't looking for, and kind of interactively learns a continuously improving machine learning model to better disambiguate what we mean when we talk about police cars. And so if we kind of go through here, you can select kind of after just sort of 2 rounds of refinement, we end up with the ability to, with relatively high precision, go through and say, yeah, this is what I want, this is what I don't want. And I'm going to review this and apply this auto tag to my whole data set. And now this becomes new structured metadata that we can build queries on and sort of search. So what ends up happening is you now kind of have the metadata available to say, hey, show me like of my auto tags for an image, show me the ones that are tagged with police cars. And now, even though not all of this is labeled, we have this metadata we can query and create slices and so on. So I'll turn it over for questions now. This type of workflow of finding an issue in the long tail, creating an auto tag from it, and then you can create a slice from it and send it off to labeling. This is how we see folks sort of debugging the long tail most efficiently.
All right, thanks so much, Russell. This was an amazing insight in this long tail debugging here. There's a question just coming in. What is object detection algorithm here? Is it YOLO 3 SSD? If you could just maybe touch on that question, there's a second part to it as well. Oh, you're muted, Russell.
Looks like I was muted. Yep. So the question is around what object detection algorithm is used. So in that particular example, it was an efficient det model doing the object detection, but in general, the sort of workflow should be agnostic to what is your model architecture, right? The whole idea is that regardless of the model architecture, the emphasis on data debugging and kind of data improvement is where you drive the highest leverage. So the kind of second part of that question, which is how do you automatically get ground truth without human eyes? That's where actually using your model and using potentially a platform that has a machine learning model being trained under the hood is super high leverage. So, you take existing ground truth, you take your model predictions and you diff them and you say, hey, where's my model really confident? Very likely to be something worthy of attention. Same for creating an auto tag.
All right, and there was one question. You did a really great job in looking at the questions during the presentation. Not sure if you actually got to that one. Does the tool provide a 2D distribution of the location of the objects in the image?
Oh yeah, it's a great question. So right now, no. You can add that as kind of custom metadata via the custom metadata API that you have in Nucleus, if that's something you're already computing, but it's something we would be looking to add in the future. It's a great suggestion.
All right, perfect. In the interest of time, let's wrap it here. Thanks so much, Russell. And we also had Marcel online from Scale. What's the best way to reach you, Russell, if people want to maybe follow up on that discussion? Should they connect on LinkedIn or email?
I'll drop my email in the chat and also drop a link if people want to kind of just sign up and upload some data and try this out themselves. It's kind of free to do. And so, yeah, thanks for having me.
Perfect. Thanks so much, Russell. Really appreciate it. All right. And with that, let's do a big switch and let's talk about recommendation systems. And with that, I'm handing over to James. Grab the screen share and awesome. Take it away.
Thanks, Antje. All right, now for something completely different. My name is James Jory. I'm a principal solutions architect with AWS, and I'm a service SA for Amazon Personalize. So I specialize in working with customers and partners on building integrations with Amazon Personalize for their personalized user experiences. So I'm going to go through if you're not familiar with Personalize, I'm going to quickly go through a few slides here that help us level set on Personalize and where it's positioned and its ability to deliver hyper-personalized recommendations. And then talk about a few of the most recent enhancements to the service. And then I'm going to switch to a live demo of a full stack retail-based or e-commerce-based web application that demonstrates the key or core use cases supported by the service. So when you think about personalization, why Amazon? Well, we've actually been at the personalization in this problem space for more than 20 years, and going back as far as 1998 to our first personalization use case on product detail pages, where we were recommending similar items based on the current item based on co-interaction data. And over the decades, we've applied personalization across all of the different channels and touch points that we have with consumers across the web apps, mobile apps, even conversational AI, different industry domains, and we've learned a lot over those decades. And some of those learnings that we've had is when we started using sort of the rule-based approach that we see a lot of AWS customers start with, but we quickly learned that rule-based systems not only fall short of, they're difficult to maintain, they're very expensive, but they also don't deliver that truly personalized experience very effectively. And so not surprisingly, machine learning became the most effective tool for delivering personalized experiences. But machine learning also brings its own set of challenges to the personalization space. The first of which is real-time recommendations. So handling cold start scenarios for both items and users, where you're looking to incorporate new items that are introduced in your catalog in recommendations as quickly as possible. And then also cold starting users who are brand new to your application or service, who you don't have any interaction history, you don't know what their interests are. And Personalize has built-in capabilities for both of those problem areas. The second is avoiding the popularity trap of always recommending what's popular to your users. And Personalize is built for hyper personalization, meaning delivering recommendations that are specific to each user's interest and looking at each user as an individual instead of grouping users into cohorts or segments. Unlike other spaces of machine learning, whether it's natural language processing or computer vision, there really isn't a single algorithm or model to rule them all. So we can't use the same model across different retail customers or media customers. And there's different personalization use cases that require different algorithms. And so with personalization, you're bringing multiple algorithms for multiple use cases within all your sort of customer touch points. This, of course, raises the complexity of personalization, where as we work with more and more cutting edge algorithms, the bar gets raised on the expertise required to not only build these algorithms, but maintain and tune them over time. So this is why we created Amazon Personalize, to target some of these use cases. And as we talk about with customers in the retail use case or industry specifically, these are some of the areas that retail customers are asking for personalization capabilities. The first is delivering sort of that homepage or that initial touch point you have with your customers when they first interact with your application. Recommended for you is a real common use case here. That's sort of the canonical personalization use case. Given a user, I want to recommend products, in this case, that this user would be interested in. And then as the user sort of goes through the consideration funnel in your application is when they're on say a detail page, helping them refine their product selection by recommending similar items that other users have interacted with or even purchased as part of their purchase journey. And for customers with long tail catalogs, discoverability can be a real challenge, where you want to be able to surface those items that maybe are less popular, but also would match the relevancy or interest of a particular user. Personalize has the ability to re-rank items. And so given a list of items and a user, we want to personalize the order or ranking of those items. And that can be used in places where you have that curated list of items, say on a category page, or you have featured products or promotional products, and you want to re-rank them for each of your users. And then leveraging your recommendation system in your outbound communication. So outbound marketing or transactional emails is another real common ask from retail customers on being able to leverage Personalize. And some nuanced use cases in the retail space are cross-selling and upselling, where you're using purchasing history based on purchase data where users have bought multiple items together. So like an iPhone with a case and headphones, being able to build a model specifically for that so that you can you encourage users to add more items to their cart for checkout. Now, these are retail use cases. We have use cases also in media and entertainment, online education, financial services. Personalize is industry agnostic, and these algorithms can be used really for any industry. And so I just was highlighting some retail use cases here, but wanted to point out that the service is definitely industry agnostic. So how does Amazon Personalize work? You start by bringing purchase data, or start by bringing data about your users and items, which can be purchase data. The data sets that we use to train models and Personalize are of three types. And the first is the activity of your users, also known as events or behavioral data. And this can include purchase data, adding to cart. In media and entertainment, it could be watching a movie or listening to a song, adding to your favorite list. This is really the signal that the most important signal that personalized algorithms are based on to understand that behavioral intent. This is the only required data set with Amazon Personalize, and it's the one that all the algorithms sort of key on for building recommendations. The second kind of data set is item metadata, and this includes details about your item. So in retail, this would be sort of your price point, your category, your size, color. In media, it might be genre, actor. In music, it would also be genre. Really the data you already have in your item catalog. This metadata is particularly useful in that item cold start scenario where we don't have behavioral data for cold starting new items. And so we fall back to looking at that item metadata as a way to find similar items. And then the third data set is user metadata. This is data about your end user. So it could be demographics, age, location, their subscription tier in your product. This is also an optional data set, but it can be brought in to help improve the quality of recommendations. Once you have your data in the service, you can bring your, I'm going to go into more detail on this, but you can bring your data into the service two ways, either through bulk or streaming APIs. And then Amazon Personalize performs all the steps you typically find in a machine learning pipeline, from processing and inspecting your data, identifying what features in your data are most meaningful for the models that it's building. It can perform hyperparameter optimization automatically. It trains and optimizes the model and then deploys it behind a real-time auto-scaling API that will auto-scale resources based on the request volume that you send to the service. So going a little bit deeper into those three data set types here, we see the three of them: interactions, items, and users. And what we find is customers typically have an analog system to each one of these data sets. So for interactions, maybe they have an analytics solution that they're using for, say, clickstream events. And for the items data set, they have a catalog management system. And for users, maybe they have a user database or microservice. You can export data from each of those systems into an S3 bucket. And CSV files are sort of the middle ground for files that file format that Personalize takes in. And you can create bulk import jobs where those bulk files are imported into the service. And this is a real common way we see for customers that are looking to bootstrap into Personalize based on historical data that they already have. The other way you can get data into the service is through streaming APIs. And so we have put events, put items, and put users are ways to incrementally update these data sets. And the real-time personalization, that put events API, is really important for getting real-time recommendations, which we'll go into on the next slide. Once your data is in the service, you create what's called a solution, and that combines a recipe or an algorithm in Personalize with your data sets and some recipe configuration. So you can control some of the hyperparameters that are part of these different algorithms. And creating a actual recommender or model in Personalize involves creating a solution version. So this is where the actual model training process takes place. And then over time, as you retrain, you'll generate more solution versions based on that solution. And this diagram only shows a single solution. If you had multiple personalization use cases, you would have multiple solutions and multiple solution versions, one for each of those use cases. Once your models are trained, your solution versions are created, it's time to get recommendations out of the service. And that can be done two ways. The first is real-time recommendations, and that's where you want to, in a request response, you want to get recommendations for a user or an item, and say display it real-time in an application. And that entails creating what we call a campaign, and that's that private API or auto-scaling endpoint I mentioned earlier. So that you can then surface recommendations in your web app, your mobile app, transactional emails, so on. When we first launched the service, a lot of customers were asking, we're finding customers were post-processing recommendations to apply business rules. And they wanted to do some filtering of recommendations before ultimately displaying them in their application. And so we created a feature called filters that allows you to sort of codify your business rules in a SQL or SQL-like language that is applied to recommendations automatically, and it's conditional. You can specify a filter or not when you're pulling recommendations. And I'll show some examples of how we see customers using filters here in a few moments. The other way you can get recommendations out of Personalize is through batch inference jobs. And customers would create an input file with thousands or millions of user IDs that they want to generate recommendations for. They would submit a batch inference job, and Personalize will generate those recommendations and write them to an output file back out in S3. And then you can include filters in batch as well. And you can take that output file and use it in some sort of downstream process. I'm showing updating a cache here if you want to cache those recommendations. But email marketing campaigns are a really common use case of batch inference jobs. So the recipes that I mentioned on the previous slide, there's really three core categories of use cases or recipes in Personalize. And the first one I want to talk about is user personalization. And this is again, sort of the canonical personalization use case, where given a user, I want to provide personalized recommendations for that user. And Personalize will start by recommending, for cold users, we'll start by recommending popular items for users that it hasn't seen before. And then when you stream events into Personalize, so in this case, a user is interacting with a sport coat, pair of shoes, and a jacket, the recommendations will become personalized in just a few seconds. And so this uses that put events API we saw on the prior slide, and shows how I'll demonstrate this in a few moments, but this is how real-time recommendations are used with the user personalization recipe. Looking a little bit deeper into the user personalization recipe, this recipe has the ability to weigh exploitation versus exploration, where exploitation is biasing towards making recommendations that are the most relevant for a given user, where exploration is we want to introduce new or cold items that may be interesting to this user, but they haven't seen before. And so this recipe allows you to weigh how much to bias towards exploration or exploitation, and you can then use that for different use cases in your application. So if you want to strongly bias towards the most highly relevant, you would have a weight of 0, or if you want to have like a discoverability aspect or use case in your application, you would use a high exploration value. The exploitation side of the algorithm uses an HRNN, a recurrent neural network algorithm behind the scenes that looks at sequence models of user behavior and the key data sets in Personalize, the interactions data set. It requires a user ID, an item ID, and a timestamp. And this is where the timestamp comes in, is we're able to create sequence models on user interactions over time to be able to understand a user's intent based now, their current intent based on what maybe they were interested in earlier. So it basically assigns more attention to those recent events and where that those real-time recommendations come in. That's combined with other information we know about the item or the user, and that turns into a learned user representation where we're able to recommend the most relevant item to that user. The second use case is related items. And this is where it's if you like, you may also like type of use case. And we have two recipes for this use case. One is called SIMS, which is based on an item-to-item collaborative filtering algorithm that it looks only at the interactions data set or the behavioral data. The second recipe is a brand new recipe just released in the last few weeks called Similar Items that also looks at the behavioral data, but takes into account item metadata. And it's a great match for use cases where you have a lot of cold items or you don't have a lot of interaction history for your users. The Similar Items recipe is able to surface more of those cold items that would also be interesting to the user. The third use case is item re-ranking. And so this is where you have that curated list of items and you want to re-rank them for a particular user. Some common uses for this is featured products, category listing page, promotional items, really anywhere you have a list of items and you want to personalize those for your user. We see it also combined with search engines quite a bit, where you take the results from a search engine like Elasticsearch or Solar, and you want to personalize the order of those for your user before displaying them. I talked about filters earlier, but I wanted to cover off some examples that we see where customers use filters in their applications. And these fall into two categories. You can use filters to either include items based on a business rule or exclude items based on a business rule. And so let's consider like a retail use case where you have products that users buy on a recurring basis. So they're more consumable based products. And you want to surface those products. Hey, would you like to buy these products again, maybe in a particular carousel of your user experience? You can use a filter that recommends items based on past purchase behavior. So items I've purchased in the past. You can also include items based on a particular brand, or category, or style. Maybe if you do product ratings, you can use filters to constrain or only include items that meet those criteria. And then the flip side of that is excluding items. So in retail, real common use cases, I don't want to recommend products that are currently out of stock. And so you can use a filter that will filter out those out of stock items based on the field in your item metadata data set. And then the opposite of buy again is if you have a catalog of items that aren't repurchased by users. And so you don't want to recommend something that a user has recently purchased. And so the recently purchased exclusion filter can be used for that. Okay, as promised, I wanted to talk about some of the newer features of the service. One capability that I mentioned that customers were post-processing recommendations to filter items to include or exclude based on a business rule. Well, another post-processing request from customers is they say that the recommendations based on relevance are of really high quality, but they have some sort of business objective that they want to use to influence recommendations. So it's basically balancing relevancy against that objective. Some good examples of this are, say, price or margin. Maybe you want to bump products further up in recommendations that are higher margin. Or private label products, or maybe some products that are lazy inventory that you want to get in front of your customers to reduce the inventory of those items. In the media and entertainment space, it's based on video duration, where you want to keep customers active on your application. So recommending items that are longer in duration is one way to do that with the optimization objective. Modeling on unstructured text is another popular request, where we have customers that don't have rich structured item metadata, but they do have really rich product descriptions. And so a new feature in Personalize is using natural language processing to extract features from unstructured text. I spoke about the new similar items recipe that looks at both behavior as well as item metadata to make similar item recommendations. Dataset export was a popular request from customers, where they were wanting to export the datasets that they stream into the service to be able to do maybe some clickstream analytics, or to do some maybe some backtesting, model verification, things like that. Being able to extract the data that's in the service was a key capability of doing that. And then finally, we released a MLOps or AIOps, we call it, solution that automates all of the steps involved with training models, importing data sets, training models, updating campaigns, running batch inference jobs. All of these are asynchronous processes that can add to the operational burden of deploying the service. And so this solution allows you to automate that through configuration, and you deploy this alongside Personalize in your AWS account. So going a little deeper on a few of those features before jumping over to the demo. Unstructured text, I mentioned extracting that meaningful information from unstructured text. So this can be product descriptions, product reviews, movie synopsis, transcriptions of audio files. This is really important when you have a lot of new items, or where you have less interaction data, or where structured metadata is not available. This feature currently is limited to English only, and it looks at the first 20,000, up to the first 20,000 characters in that description. We'll be working on adding support for other languages in the near future. So some results that we've seen with some of our test data sets. This one is with the Amazon Pantry data set from Amazon Reviews. We've seen anywhere, you look at the percent change in the far right of the offline metrics for this particular data set, is when we train solutions with and without text, we see anywhere from 20 to more than 35% improvement in the various offline metrics when we introduce text in the description or in the model. Optimization objective was that other key enhancement where you can introduce a optimization objective or a business objective into the model. And the way this is done is with a numeric value that you include in your items data set. And then you can associate a sensitivity level to how much Personalize will weight that optimization objective against relevance. And this is really important trade-off that customers are making, is they're biasing recommendations towards an objective of the business, often cases, against relevance. And so this can have a negative effect if you bias too heavily towards your optimization objective, is it can reduce the interactivity that your users have with your application, because they're no longer getting what's relevant to them. You're surfacing more what's important to the business. And so it's really important that customers understand the trade-off they're making with this. And we have an offline metric, average rewards at K, that is a measurement of how much biasing towards that optimization objective is resulting in a rewards against that objective. You can update this optimization value both in bulk import as well as with the put items API, and then Personalize will pick up these updates within 2 hours using an auto update process. And the maintaining personalized experiences with ML is that AIOps solution I mentioned. It automates all of those asynchronous processes that are involved with importing your data, training models, updating campaigns, batch inference. This really offloads a lot of that operational burden. And this is just an architecture diagram of that solution. It uses AWS step functions to perform each of those steps. And it also integrates with EventBridge and is able to notify you through outbound EventBridge events. So you can tie the steps that are going on in this solution with the rest of your architecture. Okay, I'm going to switch over to a quick demo here of an application that we have, a demo application that we built and open sourced. It's available on GitHub under AWS Samples Retail Demo Store. And this is a full stack web application that involves not only a heavy dose of Amazon Personalize, but it also has other AWS services that are involved in delivering customer experience type use cases. So Amazon Pinpoint is in here for outbound messaging, Amazon Lex for a conversational AI type of interaction. We've also just released an upgrade to this this application that involves Alexa for a curbside pickup. And so you use Alexa to place an order, a convenience store type order, and Personalize is making the recommendations, and then Amazon Pay processes the payment, and then AWS location service is used for geofencing. So when you get close to the store, it triggers an associate to bring your order out to, say, the gas pump or out to the curb. And so this is all an example of all the different capabilities that are implemented in this solution. You can deploy this in your own AWS account and get access to all the code and be able to interact with the app that I'm going to show you here in a moment. This is the architecture of some of the moving parts in this application. It's a microservice-based architecture that has a full CI/CD pipeline, and many of the services that I mentioned are highlighted here in this diagram. So when you deploy this project, you get a storefront that looks like this, and it has about 2,400 products deployed across 17 categories. 6,000 different shoppers are also deployed, and the shoppers are have different associated interests with them. We call them personas. And you can see here, I'm emulating a shopper. Her name is Brooke. She's 20 years old, and her primary interests are in tools, housewares, and apparel. And so we use this persona of these three categories to generate historical interactions that are then used to train the model and personalize. So once we train the model and Personalize takes over making those recommendations. So not surprisingly, we see here, inspired by your shopping trends, we see recommendations in the houseware, some tools, as well as some apparel recommendations. And this top portion is using the user personalization recipe. Down here, featured products is we're re-ranking a set of products in the database that are marked as featured. And so we see housewares and tools and apparel towards the front of the list, or if we scroll to the right, we see products from other categories that would be less interesting to the shopper. And I'll demonstrate how the recommendations change by selecting a different shopper. And so this is a way for you to pick one of those 6,000 other shoppers. We'll pick maybe from electronics. And so this is Larry, he's 27. He's interested in electronics, outdoors, and footwear. I'll now emulate Larry, and we see that the recommendations are completely different. So we have some electronics, footwear, some outdoors with the fishing rod here. And so you see how recommendations change based on those interests. Now to simulate the real-time aspect, I'm going to go into the developer tools here in Chrome, and I'm going to delete my local storage so that I come back to the application. And now I'm a brand new user to the site. And so this is the experience you get when you first come to this demo application. It gets a sort of a welcome splash, and you can choose to sign in or not. I'm going to skip logging in to drop in as an anonymous user. I'm not going to take the product tour, so I'm going to skip that. And so now I'm getting popular products recommended to me, noted by trending products. Let's say I'm interested in footwear today. So I'll go into that category. And as I click on different footwear products, what's happening is this application is sending a product clicked event back to Personalize using the event tracker and the put events API. So here is another event. So I've sent 3 events back to Personalize. When I go back to the home page, you see my recommendations are already starting to get adjusted based on those interactions. And so that's how quickly Personalize is able to learn from my interest. Similarly, footwear is pushed towards the front, as well as a correlated category of apparel in this case. All right, I think I will stop here. Let me check see if we have time for any questions.
Yeah, regarding time, I want to be respectful of everyone. So, but we do have some really great questions in the chat, James. So first of all, thanks so much for the great talk and the very cool demo here. I think everyone is excited to see this. We do have a couple of questions here. So if you don't mind, and maybe going through the questions in the chat and answering them in the chat while I'll transition over to Mia.
Absolutely. Thank you.
Perfect. Thanks so much, James. And everyone, if you have a couple of more questions for James, he'll stick around a little bit. So keep them coming here in the chat. And with that, let's move to the third talk for today. And I'm handing it over to Mia Chang, who will talk about how to optimize NLP inference. Mia, you can take the screen share.
Okay, sure. Let me try to share my screen. Okay, I hope you can see my slide share right now.
Yes, slides are coming up.
Okay.
Perfect.
Great. So let me start my session today. So hello, everyone. I'm Mia Chang. I work as machine learning specialist solution architect in AWS, and I'm based in Berlin, in Germany. So happy to meet you out here, no matter you're calling from like morning time or evening time. So today I would like to cover the topics about how to do the inferences optimization and with the NLP use cases on Amazon SageMaker. The content that I will cover is like why we talk about inferences and what are the common challenges that our customers sharing with us, and potentially what are the different ways to optimize your inferences. And the last one we'll talk about how to do like the more secured, more easy to adaptability setup for your model endpoints and your SageMaker develop cycles. So I assume like the attendees here that you already work with the data science project. Probably you already work with prepare data, build the model, and also later on test and training the model, later on deploy the model to the endpoint or the batch inferences. So today we are going to talk more deep about in the deployment, what are the things that you need to take care so that you can have a better ways of using the endpoint itself, and what are the ways to make it more cost effective. So to start this conversation, probably you can start to think of in your project how much cost you're spending on your training process, and how much cost you are spending on your inferences process. Okay, so probably you have that numbers in mind. Yeah, so I just found that seems like there are some like sound effects for the animation, but I didn't notice that before. So it's like quite interesting, a surprise for me as well. For the infrastructure cost, they are only 10% or less is spending on the machine learning training model, and about 90% of it are actually spending on the inferences part. So you can see from the cost-wise that the inferences are taking important part of the machine learning application cycle. So when we bring up the machine learning model to the SageMaker inferences, there are three ways that you can bring, three steps you can bring along your models. The first part is prepare your model. So prepare your model, you can train the model on the SageMaker itself, or you can train the model elsewhere. The second one, you will start to have some configuration about what types of the endpoints that you want to deploy and what are the model names, production variant, different version, or compute instances, which instances that you want to deploy. You can have the configuration right here. After you create an endpoint, then your users are able to interact with your endpoints via HTTP codes. So your users will click the button on the application. So like the one that we have had for like a personalized demo, that you can click a button on that, and then on the back end, you will interact with the actual machine learning model. And on the other hand, not only the real-time endpoint, but also you can have another option is deploy your model to the batch inferences. That means you have less requirement for the real-time responded, and you also have the ability to work with the bigger data set. So under the SageMaker endpoint, actually there's a group of load balancing setup and auto scaling group. So when your users start to interact with endpoints, and it would also trigger different scale up or scale down rules, depends on your setting. So for instance, you already know that for some part of your time, you will probably need more machine. So when you deploy your models to SageMaker endpoint, you can specify which model that you're deploying and the minimum and the maximum instances count that you want to deploy, and also what kind of the scaling criteria that you want to apply to when you want to apply the auto scaling scale up for your instances. So for example, if you found your endpoint is like really busy, then you will scale up to more instances, like 2 instances or 3 instances as your setup. And this will help you to have significant cost saving due to just the minor change for the auto scaling setup in the sense. And for people who first time is hearing like real-time inferences and batch transformations, there are several ways that you can identify which use cases that you want to apply for them more. For the real-time inferences, usually would be your go-to choices when you need a persistence endpoint. While batch transformation, that you will use it for, you don't need a persistent endpoint, and then also you want to inference with a large data set. So that is usually how we identify like which type of the deployment you want to choose. And there's also the upcoming synchronized inferences choice that you can specify it under the real-time SageMaker endpoint setup. When you deploy the endpoint, you can also specify you want to deploy the synchronized inferences, and it's help you to work with computer vision use cases, NLP use cases, especially when you take a longer time to have your prediction on endpoint. Okay, so before jumping into the customer challenges, I want to have a small survey in our chat window. You can put +1 if you already have the experience to deploy your model and then you're already happy with your current setup. Or you can put +0 if you have no zero deployment yet. You only trained your model on your computer and you are the only one that users for your model at the moment. And you can also put -1 if you are not happy for your current setup with your endpoint setup, and then you can also probably mention about the reasons why you are not happy with your current setup. So I will give you a few seconds to put your states on that. I saw some of the +0, and I saw people that happy. Bedent are happy with his or her setup for deployment. Okay, cool. So some of the people that you probably haven't had your model deployment, so also during the sharing today, then you can also know during the deployment, what are the things to look for. So let me jump to the next one. What are the common, like the challenges that when customer come to us, they mention to us? The first one, they will talk about SLA, to talk about the latency, throughput, and different workloads that have to work with. And also talk about the models. And if you have a different version of the models, if you apply your models to different markets, and what are the different cases, how to do the model management. And also the compute, which instances type I would like to choose would be the CPU one, the GPU one, and is there other options other than CPU and GPU, other options, or is there any ways I can set up my infrastructure better? And people also talk about like how I can do the data management better for pre-processing, post-processing, and also the cost-wise and security topics. So today we won't cover all of them, otherwise it will extend to like not only 30 minutes, but will become like an hour, 2 hours, or even 3 hours conversation for this one. And today I will focus more on when you have the machine learning model, and later on, what are the options that you can choose from the compute instances type, and also what are the ways you can monitoring so that you can go back to know how good or how bad your deployment is, and you know what to adjust differently with the metrics that you have. And also the last one, I will also talk a bit about the compliance, so that if you are working in some of the industry which is more strict to compliance or auditability, that you definitely will need to keep tracking on who is interact with the SageMaker with which API, and how many users are actually using your endpoint, and how good or how bad your endpoint behaves. So this will be the overview when you want to deploy your model. When I talk about optimize the inferences, usually I will start from 3 aspects. The first one is talk about would be the networking part. The second one would be software and hardware. So from the networking part, usually when you are thinking this part is also relevant to your model, which markets that you're serving to. For example, if you are based in US, if you are based in UK, and then probably your customer is in different region that you deploy to, you will need the global accelerators can help you to speed up when you work with the customers in different places. And also the same as when you work with the customers in different regions, or you have a different setup in AZ. So in the networking part, usually will be more broader discussion. You have to across different team discussion related to networking setup. And if you work as a data scientist, from your perspective, then you can speed up, could be from software part and hardware, which instances type you are going to deploy later. So most of the time that the conversation will focus on the software optimization and hardware optimization a bit more. So if you already are AWS users, you probably already know, like we have a lot of different types of the instances that you can spin up when you're using EC2, but also when you want to deploy your machine learning model, you can also choose which type of the instances you want to deploy to. So the most common that people will mention about would be the CPU one and the GPU one. So the CPU one, usually if you want to deploy the really small model, like the one that you had with the scikit-learn, and people will probably deploy the neural network machine learning model on the GPU instances, but also there's other options other than just only CPU and GPU setup. There's also elastic inferences. So it's optimized the chips that optimized instances that you can deploy together with the CPU. So together work with the CPU and one optimized instances, then you'll be able to serve the middle size of the models. So for some of the relevantly simple models, for example, like if you have less image class or text class that you want to classify, then you can choose the CPU with elastic inferences as the mid-size use cases so that it's more cost effective and also bring along really good numbers of the latency. And the other one is the inference shot. So the inference shot is the one that work with the really high throughput, high performance, and low cost use cases. So with this 4 different instances type that you probably would like to identify them. For example, if you just use the CPU only, GPU only, or you work with the CPU with elastic accelerators, elastic inferences accelerators, or you work with inferential. And it really depends on the use cases that you have. For instance, when you deploy the model, you have to also talk with your stakeholders. And they probably will mention about what our customers' expectations there. Then you can talk to them. Are you concerned about what's the throughput latency, or are you concerned about the cost? So you can bring this table and talk with your stakeholders. You can sit down together to think which type of the deployment type would be most fit your use cases. So when you bring along your original model file, how you can work with elastic inferences and inferential instances, then you can use a job in the SageMaker called Amazon SageMaker NEO. So you can use the SageMaker NEO to help you to optimize your model. So you can see from this table, the orange one is the baseline, is the original model, and the blue one is the NEO compiled model. So you can see the milliseconds, the performance for the models improved, let's say, 4 times, 5 times, or close to 6 times better than the original model. So even you don't start to use the GPU, you just choose the original CPU one with the compiled model, then you're able to achieve better performance only with the compiled model with NEO. So usually the next step, you will start to think, okay, how can I work with the SageMaker NEO? How does the code will look like when I start to doing the experiment? So that when you start to initiate your model with the estimator, you mentioned about your model is a PyTorch one, TensorFlow one, or different frameworks that you're using. You specify your framework, and then you bring along your pre-trained model. Your model is prepared. You bring along now start to compile the job. So in the compile job, that means under the hood we will call out the SageMaker NEO. And then you have to specify which type of the instance that you want to deploy later, and then your input shape of your machine learning model, and also where are you going to store to save your compiled model, and also the more details like the job name and compile the max run and etc. So now you have an overview for like what would be your first step to start your model optimization. You probably just start simply just to compile your model with the NEO and try to deploy it with the same instances that you deployed before, and then you just test how much is improved with the model compilation. Okay. So now I want to share like 2 QR codes in case you would like to start to work with NEO, but you already start to think like which version that I work with my framework and does that support the CPU or GPU instances that I want to deploy to. and what are the inferential instances type, what's the support for each of them. So for example, I don't really remember them all in my heart. It's like whole table, but I always will have a look when I need them. So you can just keep the QR code or link with you, and then later on you can look it up as you want. It's also on the Amazon document. Okay, so that would be the first one, how to work with the NEO. So after you got the compile model, the next one, if you want to work with the elastic instances, you can just keep the same code as you had. And if you want to work with inferential, give me the second. If you want to work with inferential, which is the instances that we optimize for inference use case, then you will need a SDK called AWS Neuron. So for example, let's take the transformers as example. So when you have the Hugging Face transformers, you have the tokenizers there, you have the model there. So you do all the initialization the model with your current setup. And later on, you need to add 2 lines of the code. One is the import torch neuron. And the second line of the code is mentioned about when you use the model prediction that you will run through with the PyTorch neuron, so that you will interact with the inferential one, and then you will run the prediction for you. So that's the changes when you run the prediction with inferential instances. And in this one, I also put links here so that you know like which models that I'm presenting here, and later on you can test it out later. And this is the testing result. Compare the before and after, and work with the inferential instances. So this will gives you an overview for like what's the numbers, what's the cost for each of the inferences, and also the throughput number for the inferential instances, and also the G4DN instances. And you can use it to compare when you are using the PyTorch and NLP model on that. Okay. And when mentioned about the software optimization, there's also for people who work with the TensorFlow model, there's also a way that you can change a small line in your inferences applied in the SageMaker prediction script. You change your code from the raster code to the gRPC code, which can also help you to reduce the latency by 40%. So you can choose from the hardware improvement, as I mentioned earlier, and you use the compilation, and also choose the different instances type. And for this one is the software optimization. You change how you interact with the model serving part. So when you work with your own model project, then you can list a table like this one. You can start to list down CPU, GPU, or the elastic inferences one or the inferential one. And each of them, you have a different version of the model. And then you can have your original model, and then compile with NEO, deploy to different instance type, and then you can get the benchmark numbers for your own model, so that you can have a comparison about your use cases deployed to which inferences type, and how good or how bad it performs, and what's the latency, the cost for it. And then you will get a table look like this one. Is this compiled or not? Is this instances type is on itself, or is with some elastic inferences type optimization? And how many CPU, RAMs, and GPU? These 3 lines that you can get just from the document, AWS document. And these numbers that you can run when you run through the experiment. I put the code there as well, so you can follow with. And later on, you can bring this table again to your stakeholder side to talk about what's you're most concerned for this project. It could be the cost, could be per 1 second, how many characters that you can run through, and for like different options or different concerns that you have with your team, so that you can talk through with this table, and then you will know which type of the instances and would be your best choice for your project. Sometimes you will think like always the first is the best one. That's one of the possibilities. And another possibility could be probably there's just really minor differences between option 1 and option 2, but the cost is quite different, so that it's that trade-off that you can choose one over the other. So bring up this table, just give you an overview for like when you want to choose what type of the instances would be the one that you go to, you can have an overview on it. Okay. The next, I think we also talk a lot about the software and the hardware one and how to bring an overview table for that. And the last but not least, I want to mention about, besides the functionalities that we have, the SageMaker for the model monitor, there's also other 2 services that you can work together with the SageMaker to make your whole development cycle more secured and compliant. The first will be to trace which SageMaker API request that's been calling by the different developers, so that you can have a better overview for like which developers is doing what actions on different services. For example, like this one. So if there's a developers called Bob, and then he starts to open the SageMaker notebook instances on the SageMaker. And then in the CloudTrail, you can have a look like this one. So the event detail will telling you which users are calling which actions on the SageMaker. So that's what's the benefit of this one. So if you have the correct rules set up for your developers or for your development group, then you are able to monitor is that everyone works the environment, they only access to the environment they can work with. Did they also behave on the actions that they are allowed to? Or for example, if you have an intern or just someone just joined the team just 3 days, but they already can start to behave like deployment the model to production, there will be like really not secure setup. But with this one, then you can just find out like who is doing what on the systems, so that you can have a better view for knowing the whole the team's work environment setup and how people to collaborate together. And not only for the API monitors, then you can also knowing like if the artifact is being changed. So this one is like the resources. Someone opens the resources, someone deploys the resources. And then you can also use it to monitor things like, is anyone push the model? Is there anyone to deploy the model or change the model on production? So things like that could be monitored through the CloudTrail. And the next one is talk about logging and monitoring. This one will be, most of you, I think, would be more familiar, is using the CloudWatch. So usually we go to CloudWatch to check our logs, and also it's a good place to set up alarms and notification if you found that there's abnormal behaviors for your endpoint. And for example, like response not the 200 code, or you are seeing like the latency is dropping or enhancing during the different times, so that you can have an overview for your endpoint, how does it behave with the dashboard. so that with the CloudTrail and then the CloudWatch, you can have an overview for how's your systems going, no matter from development perspective or after deployment, that which application is calling your endpoint and so on. So not only with the SageMaker, the endpoint monitor, but also you can work with CloudWatch and CloudTrail to do that. Okay, so I think that's most of things that I covered. To summarize today's topic that we've gone through, there are 3 ways to optimize the model: the hardware, the software, and the networking. The most of the parts that we can do from data scientist or developers perspective, most of the time we can focus on the software optimization and hardware choosing, which type of the instances that we are deploying to. So that will help you to have the right size for your model and also the right size for your instance type as well. So you will have things like this one, the right sizing for both the model and the instance type you deployed. And you can also think to work with the inferential instances if your workload is on the huge data set with the inferential. And if you have the middle size of the model, then you can think of the CPU with the elastic inferences. It's cost similar as the CPU one, but it will also have the really good result when you run the NLP and also computer vision model on that. So besides this several points, you can think of like where you're going to deploy your endpoint. Most of the time we'll just bias to recommend you to deploy on the SageMaker endpoints. But if you don't want take the benefit features from the endpoint, you can also think to deploy your model only on Lambda or on the Kubernetes on AWS. That's also the possible choices. And then you can work with the workloads that you're familiar with. The last one is to think of like to do the logging and monitoring, not only with the SageMaker, but also with other applications as well, that can help you to have a better overview for your teamwork and also for the usage of your endpoint. So I think that's it. That's the things that I would like to cover for today's sharing. Any questions?
Thanks so much, Mia.
Yeah,
sure. Overview. We had one brief question here, more around integration with Kubernetes on the serving side. So not sure if you want to share some thoughts there, or we can probably also discuss that.
Okay. Yeah, so I can share some of experience around like deploy to the Kubernetes one. So usually if you want to deploy to the Kubernetes one rather than the SageMaker one, then you will need a great team, DevOps team work together with you. Otherwise, from the data scientist perspective, you have to take care of the model, you have to take care of the cluster management, and then there will take a lot of time to maintain the cluster. So if you have a group of people that they are really happy to maintain Kubernetes cluster with you together, then you can think for this option. Because I know for some of the companies that they already have the setup like Grafana dashboard, they have centralized the dashboard to monitor all their applications. So in the sense, they probably already have the really strong setup for Kubernetes clusters and so on. And in this sense, will make more sense if you want to put the things on Kubernetes cluster. And if no, probably I will recommend you to work more with the SageMaker endpoints. Yeah.
All right, perfect. And we're interested in hearing your use cases if you do have a specific use case in mind, of course.
Exactly.
All right. Yeah, thanks so much, Mia. Thanks everyone for sticking around in today's a little bit longer session. And also thanks to James. He responded to all of the questions we had around the personalization session earlier. So thanks, James, for sticking around and answering those as well. And with that, it's a wrap for today. Thanks so much, everyone, for joining. Really appreciate all of the talks and all of the great questions and discussions we had. Thanks so much.
Thank
Have
you.
a great day, everyone.